And so we can also fill out the gradients with respect to W1 and X1 here in exactly the same way. And so one thing that I want to note is that, right, when we're creating these computational graphs, we can define the computational nodes at any granularity that we want to. So in this case, we broke it down into the absolute simplest that we could, right? We broke it down into additions and multiplications. It basically can't get any simpler than that. But in practice, right, we can group some of these nodes together into more complex nodes if we want, as long as we're able to write down the local gradient for that node, right? And so as an example, if we look at a sigmoid function, so I've defined the sigmoid function in the upper right here, of a sigmoid of x is equal to 1 over 1 plus e to the negative x. And this is something that's a really common function that you'll see a lot in the rest of this class. And we can compute the gradient for this. We can write it out, and if we do actually go through the math of doing this analytically, we can get a nice expression at the end. So in this case, it's equal to 1 minus sigma of x, so the output of this function, times sigma of x, right? And so in cases where we have something like this, we could just take all the computations that we had in our graph that made up this sigmoid, and we could just replace it with one big node that's a sigmoid, right? Because we do know the local gradient for this gate. It's this expression d of the sigmoid of x over dx, right? So basically the important thing here is that you can group any nodes that you want to make any sorts of a little bit more complex nodes, as long as you can write down the local gradient for this. And so all this is basically a trade-off between how much math that you want to do in order to get a more kind of concise and simpler graph, right, versus how simple you want each of your gradients to be, right? And then you can write out as complex of a computational graph that you want. Yeah, question? So they could also be connected into a single addition node. So the question was, is there a reason why W0 and X0 are not connected with W2? All of these additions just connected together. And yeah, so the answer is that you can do that if you want. And in practice, maybe you would actually want to do that because this is still a very simple node, right? So in this case, I just wrote this out into as simple as possible, where each node only had up to 2 inputs. But yeah, you could definitely do that. Any other questions about this? Okay, so the one thing that I really like about thinking about this like a computational graph is that I feel very comforted, right? Like anytime I have to take a gradient, find gradients of something, even if the expression that I want to compute gradients of is really hairy and really scary, whether it's something like the sigmoid or something worse, I know that I could derive this if I want to, but really, if I just sit down and write it out in terms of a computational graph, I can go as simple as I need to always be able to apply backprop and the chain rule and be able to compute all the gradients that I need. And so this is something that you guys should think about when you're doing your homeworks, as basically, anytime you're having trouble finding gradients of something, just think about it as a computational graph, break it down into all of these parts, and then use the chain rule. Okay, and so so we talked about how we could group these set of nodes together into a sigmoid gate, and just to confirm that this is actually exactly equivalent, we can plug this in, right? So we have that our input here to the sigmoid gate is going to be 1 in green, and then we have that the output is going to be here 0.73, right? And this will work out if you plug it into the sigmoid function. And so now if we want to do, if we want to take the gradient and we want to treat this entire sigmoid as one node, now what we should do is we need to use this local gradient that we've derived up here, right? 1 minus sigmoid of x times the sigmoid of x. So if we plug this in, and here we know that the value of sigmoid of x was 0.73. So if we plug this value in, we'll see that the value of this gradient is equal to 0.2. Right, and so the value of this local gradient is 0.2. We multiply it by the upstream gradient, which is 1, and we're going to get out exactly the same value of the gradient with respect to before the sigmoid gate as if we broke it down into all of the smaller computations. Okay, and so as we're looking at what's happening, right, as we're taking these gradients going backwards through our computational graph, there's some patterns that you'll notice where there's some intuitive interpretation that we can give these, right? So we saw that the add gate is a gradient distributor, right? When we pass through this addition gate here, which had 2 branches coming out of it, it took the gradient, the upstream gradient, and it just distributed it, passed the exact same thing to both of the branches that were connected. So here's a couple more that we can think about. So what's a max gate look like? So we have a max gate here at the bottom, right, where the inputs coming in are z and w. Z has a value of 2, w has a value of -1, and then we took the max of this, which is 2, right, and so we passed this down into the remainder of our computational graph. So now if we're taking the gradients with respect to this, the upstream gradient is, let's say, 2 coming back, right? And what does this local gradient look like? Yes. Right. Exactly. So the answer that was given is that z will have a gradient of 2, w will have the value gradient of 0. And so one of these is going to get the full value of the gradient just passed back and routed to that variable, and then the other one will have a gradient of 0. And so we can think of this as kind of a gradient router, right? So whereas the addition node passed back the same gradient to both branches coming in, the max gate will just take the gradient and route it to one of the branches. And this makes sense because if we look at our forward pass, what's happening is that only the value that was the maximum got passed down to the rest of the computational graph, right? So it's the only value that actually affected our function computation at the end. And so it makes sense that when we're passing our gradients back, we just want to adjust what, flow it through that branch of the computation. Okay, and so another one, what's a multiplication gate, which we saw earlier? Is there any interpretation of this? Okay, so the answer that was given is that the local gradient is basically just the value of the other variable. Yeah, so that's exactly right. So we can think of this as a gradient switcher, right? A switcher and I guess a scaler, where we take the upstream gradient and we scale it by the value of the other branch. Okay, and so one other thing to note is that when we have a place where one node is connected to multiple nodes, the gradients add up at this node, right? So at these branches, using the multivariate chain rule, we're just going to take the value of the upstream gradient coming back from each of these nodes, and we'll add these together to get the total upstream gradient that's flowing back into this node. And you can see this from the multivariate chain rule, and also thinking about this, you can think about this, that if you're going to change this node a little bit, it's going to affect both of these connected nodes in the forward pass, right? When you're making your forward pass through the graph, and so then when you're doing backprop, right? Then now the both of these gradients coming back are going to affect this node, right? And so that's why we're going to sum these up to be the total upstream gradient flowing back into this node. Okay, so any questions about backprop going through these forward and backward passes? Right, so the question is, we haven't done anything yet to update the values of these weights. We've only found the gradients with respect to the variables. That's exactly right. So what we've talked about so far in this lecture is how to compute gradients with respect to any variables in our function, right? And then once we have these, we can just apply everything we learned in the optimization lecture, last lecture, right? So given the gradient, we now take a step in the direction of the gradient in order to update our rate, our parameters, right? So we can just take this entire framework that we learned about last lecture for optimization, and what we've done here is just learn how to compute the gradients we need for arbitrarily complex functions, right? And so this is going to be useful when we talk about complex functions like neural networks later on. Yeah. Yeah, so I can write this maybe on the board. Right, so basically if we're going to have, let's see, if we want to have the gradient of f with respect to some variable x, right, and let's say it's connected through variables, let's see, I, we can basically, right, so this is basically saying that if x is connected to these multiple elements, right, let's say in this case different QIs, then the chain rule is taking all, it's going to take the effect of each of these intermediate variables, right, on our final output f, and then compound each one with the local effect of our variable x on that intermediate value. Right, so yeah, it's basically just summing all these up together. Okay, so now that we've done all these examples in the scalar case, we're going to look at what happens when we have vectors, right? So now for variables x, y, and z, instead of just being numbers, we have vectors for these. And so everything stays exactly the same, the entire flow. The only difference is that now our gradients are going to be Jacobian matrices, right? So, so these are now going to be matrices containing the derivative of each element of, for example, z with respect to each element of x. Okay, and so to so give an example of something where this is happening, right? Let's say that we have our input is going to now be a vector. So let's say we have a 4096 dimensional input vector. And this is kind of a common size that you might see in convolutional neural networks later on. And our node is going to be an element-wise maximum, right? So we have f of x is equal to the maximum of x compared with 0 element-wise. And then our output is going to be also a 4096 dimensional vector. Okay, so in this case, what's the size of our Jacobian matrix? Remember I said earlier the Jacobian matrix is going to be, like each row it's going to be partial derivatives, a matrix of partial derivatives of each dimension of the output with respect to each dimension of the input. Okay, so the answer I heard was 4096 squared, and that's correct. So this is pretty large, right? 4096 by 4096. And in practice, this is going to be even larger because we're going to work with mini batches of, for example, 100 inputs at the same time, right? And we'll put all of these through our node at the same time to be more efficient. And so this is going to scale this by 100, and in practice, our Jacobian is actually going to turn out to be something like 409,000 by 409,000, right? So this is really huge and basically completely impractical to work with. So in practice, though, we don't actually need to compute this huge Jacobian most of the time. And so why is that? Like, what does this Jacobian matrix look like? If we think about what's happening here, where we're taking this element-wise maximum, and we think about what are each of the partial derivatives, right? Which dimension of the inputs affect which dimensions of the output? What sort of structure can we see in our Jacobian matrix? Okay, so I heard that it's diagonal. Right, exactly. So because this is element-wise, right, each element of the input, say the first dimension, only affects that corresponding element in the output, right? And so because of that, our Jacobian matrix, which is just going to be a diagonal matrix, right? And so in practice, then, we don't actually have to write out and formulate this entire Jacobian. We can just know the effect of x on the output, right? And then we can just use these values, right, and fill it in as we're computing the gradient. Okay, so now we're going to go through a more concrete vectorized example of a computational graph, right? So let's look at a case where we have the function f of x and w is equal to basically the L2 of w multiplied by x. And so in this case, we're going to say x is n-dimensional and w is n by n. Right, so again, our first step, writing out the computational graph. Right, we have w multiplied by x and then followed by, I'm just going to call this L2. And so now let's also fill out some values for this. So we can see that, let's say have w be this 2 by 2 matrix and x is going to be this two-dimensional vector. Right, and so we can say, label again our intermediate nodes. So our intermediate node after the multiplication is going to be q. We have q equals w times x, which we can write out element-wise this way. Right, the first element is just w11 times x1 plus w12 times x2 and so on. And then we can now express f in relation to q. Right, so looking at the second node, we have f of q is equal to the L2 norm of q, which is equal to q1 squared plus q2 squared. Okay, so we fill this in, right? We get q, and then we get our final output. Okay, so now let's do backprop through this, right? So again, this is always the first step. We have the gradient with respect to our output is just 1, right? Okay, so now let's move back one node. So now we want to find the gradient with respect to q, right? Our intermediate variable before the L2. And so q is a two-dimensional vector. And what we want to do is we want to find how each element of q affects our final value of f, right? And so if we look at this expression that we've written out for f here at the bottom, we can see that the gradient of f with respect to a specific qi, let's say q1, is just going to be 2 times qi. Right? This is just taking this derivative here. And so we have this expression with respect to each element of qi. We could also, write this out in vector form if we want to. It's just going to be 2 times our vector of q, right, if we want to write this out in vector form. And so what we get is that our gradient is 0.44 and 0.52, this vector. Right? And so you can see that it just took q and it scaled it by 2. Right? Each element is just multiplied by 2. So the gradient of a vector is always going to be the same size as the original vector, and each element of this gradient is going to, it means how much this particular element affects our final output of the function. Okay, so now let's move one step backwards. Right? What's the gradient with respect to w? And so here again, we want to use the same concept of trying to apply the chain rule, right? So we want to compute our local gradient of q with respect to w. And so let's look at this again element-wise. And if we do that, let's see what's the effect of each q, right? Each element of q with respect to each element of w, right? So this is kind of the Jacobian that we talked about earlier. And if we look at this in this multiplication, q is equal to w times x, right? What's the derivative or the gradient of the first element of q, so our first element up top, with respect to w11. So q1 with respect to w11. What's that value? x1. Exactly. Yeah. So we know that this is x1, and we can write this out more generally of the gradient of qk with respect to of wij is equal to xj. Right? And then now if we want to find the gradient with respect to of f with respect to each wij, so looking at these derivatives now, we can use this chain rule that we talked to earlier, where we basically compound df over dqk for each element of q with dqk over wij for each element of wij, right? So we find the effect of each element of W on each element of Q and sum this across all Q. And so if you write this out, this is going to give this expression of 2 times Qi times xj. Okay, and so filling this out, then we get this, this gradient with respect to W. And so again, we can compute this each element wise, or we can also look at this expression that we've derived and write it out in vectorized form, right? So, okay, and remember, the important thing is always to check the gradient with respect to a variable should have the same shape as the variable. And so this is something really useful in practice to sanity check, right? Like once you've computed what your gradient should be, check that this is the same shape as your variable. Because again, the element, each element of your gradient is quantifying how much that element is contributing to your, affecting your final output. Yeah. The bold size, the bold size 1 is an indicator function. So this is saying that it's just 1 if k equals I. Okay, so let's see. So we've done that. And so now just let's see, one more example. Now our last thing we need to find is the gradient with respect to Qi. So here, if we compute the partial derivatives, we can see that dqk over dxi is equal to wki, right? Using the same way as we did it for w, and then again we can just use the chain rule and get the total expression for that. Right, and so this is going to be the gradient with respect to x, again, of the same shape as x, and we can also write this out in vectorized form if we want. Okay, so any questions about this? Yeah. So we are computing the Jacobian. So let me go back here. Right, so if we're doing, so we have these partial derivatives of qk with respect to xi, right? And these are forming your the entries of your Jacobian, right? And so in practice, what we're going to do is we basically take that, and you're going to see it up there in the chain rule. So the vectorized expression of gradient with respect to x, right? This is going to have the Jacobian here, which is this transposed value here. So you can write it out vectorized form.
지난 시간에 설명했던 컴퓨테이셔널 그래프입니다. 여기에서 컴퓨테이셔널 노드는 우리가 원하는 그래뉴라리티, 세분화로 설정할 수 있습니다. 뉴럴 네트워크에서는 종종 시그모이드 펑션이 사용됩니다. 시그마 x는 1 나누기 1 더하기 2의 마이너스 x승으로 주어집니다. 아래 컴퓨테이셔널 그래프에서는 4개의 노드가 시그모이드 게이트의 역할을 하고 있는 것을 보여주고 있습니다. 시그모이드 펑션에서 x에 대한 그라디언트 시그마를 계산하면 1-시그마 곱하기 시그마가 됩니다. 이 식을 아래 시그모이드 게이트에 대입하면 0.2의 그라디언트 값을 얻을 수 있습니다. 이처럼 그래뉴라리티가 변한다 하더라도 이전에 배웠던 백프로퍼게이션 방법을 여전히 사용할 수 있습니다. 우리는 백워드 플로우에서 어떤 패턴들을 발견할 수 있습니다. 예를 들면 더하기, 애드 게이트 같은 경우에는 그라디언트의 디스트리뷰터 역할을 합니다. 즉, 업스트림 그라디언트를 받아서 두 개의 브랜치를 통해서 같은 값을 전달합니다. 반면에 맥스 게이트 같은 경우에는 업스트림 값을 맥스 값을 갖는 하나의 인풋에만 전달합니다. 우리는 이러한 패턴을 맥스 게이트의 그라디언트 라우러라고 이야기할 수 있습니다. 한편 멀 게이트 같은 경우에는 그라디언트 스위처의 역할을 합니다. 두 개의 인풋 브랜치의 그라디언트를 계산하는 데 있어서 두 개의 인풋 값이 서로 스위치됩니다. 지금까지 패턴에 더해서 만일에 하나의 노드가 멀티플 노드에 연결된 경우 각 브랜치의 그레디언트가 서로 더해지게 됩니다. 지금까지는 스칼라에 대한 그레디언트를 다루었기 때문에 이제는 개념을 확장해서 벡터에 대한 그레디언트가 어떻게 동작하는지를 보도록 하겠습니다. 이제는 x, y, z가 스칼라가 아니라 벡터라는 것을 제외하고 전체적 흐름은 이전과 같습니다. 단 하나 큰 차이는 그라디언트가 더 이상 숫자가 아니라 자코비안 매트릭스라는 것입니다. 이 매트릭스는 x 벡터 엘리먼트에 대한 z 벡터 엘리먼트의 데리버티브로 정의됩니다. 벡터라이즈드 오퍼레이션의 사례입니다. 4096 디멘전의 인풋 벡터, 4096 디멘전의 아웃풋 벡터, fx는 max 0x로 이루어집니다. 여기서 자코비안 매트릭스를 구현한다고 하면 x에 대한 f의 그라디언트 값을 구해야 됩니다. 이때 자코비안 매트릭스의 사이즈는 4096개의 인풋 벡터 디멘전에 4096개의 아웃풋 벡터 디멘전을 곱한 매트릭스가 필요합니다. 만약 우리가 100개의 이그젬플을 가진 미니 배치를 프로세스한다고 하면 40만 곱하기 40만 매트릭스로 상당히 큰 크기가 될 것입니다. 벡터라이즈드 이그젬플을 수식으로 표현하면 x는 R의 n승에 속하는 원소이고 웨이트 매트릭스 W는 R의 n승 곱하기 n에 속하는 원소입니다. 이 함수를 컴퓨테이셔널 그래프로 다음과 같이 표현할 수 있습니다. Intermediate Variable로 Q를 W times X로 정의할 수 있습니다. 또한 이 Q는 L2 노드의 인풋이 됩니다. 다음과 같이 디멘전이 2이고 W와 X 값이 주어질 때 우리는 Q를 계산하고 F 값을 계산할 수 있습니다. L2의 아웃풋은 스칼라지만 L2의 인풋은 벡터이기 때문에 우리는 QI에 대한 F의 그라디언트 값을 먼저 구합니다. 그 결과 이 QI를 얻었는데 이를 벡터로 전환하면 이 Q가 됩니다. 이 식을 이용해서 L2의 인풋 벡터에 대한 그라디언트 값을 구한 결과 0.44, 0.52가 나왔습니다. 다음 단계로는 엘리먼트 Wij에 대한 엘리먼트 QK의 그라디언트 값을 구합니다. 그 결과 1k equal i 곱하기 xj라는 값을 얻었습니다. 여기서 1k equal i는 k가 i와 같을 때 1이고 k가 i와 다를 때는 0이라는 뜻입니다. 체인 룰을 적용하면 엘리먼트 Wij에 대한 f의 그라디언트는 2qi 곱하기 xj가 됩니다. 이 식을 바탕으로 모든 가능한 ij에 대해서 계산을 하면 W 매트릭스에 대한 f의 그라디언트 값을 보시는 것처럼 얻을 수 있습니다. 이러한 엘리먼트에 대한 식을 벡터와 매트릭스에 대한 식으로 표현하면 W에 대한 그라디언트 f equal EQ 곱하기 X 트랜스포즈가 됩니다. always check, 여기서 항상 체크해야 될 것은 f의 그라디언트가 input x의 트랜스포즈에 EQ를 곱한 것이기 때문에 input variable x와 같은 shape을 가져야 한다는 것입니다. 다음은 엘리먼트 xi에 대한 엘리먼트 qk의 그라디언트입니다. 이 값은 wki입니다. 체인 룰을 적용하면 x에 대한 f의 그라디언트 값은 시그마 k의 eqk 곱하기 wki로 주어집니다. 엘리먼트에 대한 식을 벡터와 매트릭스에 대한 식으로 표현하면 x의 그라디언트 f equal EW 트랜스포즈 곱하기 Q가 됩니다. 이번 시간에 우리는 스칼라 형태를 확장해서 벡터 형태의 backward propagation과 자코비안 매트릭스에 대해서 배웠습니다. 다음 시간에는 이러한 기본 개념들을 바탕으로 뉴럴 네트워크가 어떻게 구현될 수 있는지에 대해서 알아보도록 하겠습니다.